Assalamualaikum warahmatullahi wabarakatuh and a very good morning. So, the previous topic you have learned about the basic partial differential equation, where the differential equations are widely used to observe from a simple to complex system. So, for the first application of PDE that we are going to learn is about heat equation. We are going to learn about the heat flow of a long uniform rod, where we can describe how the heat distributed along the rod and how the heat evolves over time. So the heat flow of this is represented as this partial differential equation, where del u over del t equals to k squared del squared u over del s squared. This equation, it depends on the initial distribution of temperature and the second one, it depends on the physical properties of the rod, where we call it as thermal diffusivity, where it measures the rod's rate of the local conduction. This thermal diffusivity is represented as k square. Okay, so this equation, this is a one-dimensional heat equation because it involves one spatial dimension, which is x, whereas t is represented as time. So if you want to plot or if you want to solve the 2D heat equation, where a 2D heat equation can be write as del u over del t k squared del squared u over del s squared plus del squared u over del y squared. It means that it involves two partial dimensions, which is x and y. And for 3D, the heat equation will be del u over del t equals to thermal diffusivity times with del squared u over del x squared plus del squared u over del y squared plus del squared u over del z squared. Okay, but for this chapter, we only focus on one-dimensional heat equation in terms of this equation. So to obtain the solution of this PDE, where you need to solve this PDE using the method of separation of variables, so that from here we can get the solution in terms of u, x, and t. So from this equation, we can get the temperature distribution along the rod. How does the temperature distributed along this rod? And the second one is we can get the temperature distribution over time. For example, this figure 2, where the blue line shows the temperature distribution when T is equals to 0, and the green line shows the temperature distribution at T equals to 0.05. So it means that when X is equals to 0.2, the temperature distribution is here. When at X equals to 0.4, the temperature distribution is like this. And when X is equals to 0.8, the temperature distribution is like this. In heat equation, there are three cases that we need to consider. The first one is the heated rod with zero temperature at endpoints. The second one is heated rod with insulated endpoints. And the third one is heated rod with non-zero temperature at endpoints. So we will go through one by one. For the first case, where the heated rod with zero temperature at endpoints. So for this case, let we assume that the rod extends from x equals to 0 to x equals to L. So the length of the rod is x is equals to L. The second assumption is the rod is uniform, that is, its mass per unit volume is constant. The third one is the lateral or curve or surface of the rod is perfectly insulated. That means that no heat escapes from the surface. And the fourth one is the thermal diffusivity, which is K square, is a constant. The fifth is the flow of heat within the rod takes place only in the x direction. So this means that it is a one-dimensional with x direction. 6 is the temperature at the ends of the rod is maintained as 0. So here, this is the case where, for the first case, where the heated rod with 0 temperature at end points. The 7 is no heat is being generated within the rod. And the last one is the initial temperature distribution along the rod is defined as Fx. So we can represent this as this figure, where at x equals to 0, U is equals to 0 degree, where U is defined as temperature distribution at x equals to 0. And when x is equals to L, the temperature distribution is equals to 0. With all the assumptions that has been made from the previous slide, we can represent it as the PDE in terms of this equation, del U over del T equals to K squared del square U over del S squared, where K square is a constant, and the boundary condition is given as U0T equals to 0, and when x equals to L, the temperature is equals to 0. And the initial condition when T is equals to 0, the temperature distribution is equals to function of x. Solving this using the method of separation of variables, we will get the solution of this PDE in terms of this solution, where the solution of this PDE with the given boundary condition and initial condition is equals to the summation of dn times sine n pi x over L e to the power of negative n square pi square k square t over L square, where dn is the Fourier sine series coefficients, given that dn is equals to 2 over L times with the integration of fx sine n pi x over L dx, where the limit is from 0 up to L. So L here represents the length of the material, the length of the rod. Fx is the function of initial condition. And the last thing that is important is K square, where K square is the thermal diffusivity, where you can get this from the PDE. So you need to identify these three values in order to solve the PDE. And then once you have all these value, you can substitute into the Fourier sine series coefficients, which is dn. And once you get dn, you will substitute into this solution in order to get the solution of the PDE, which is UXT. In this video, I'm not going to show you how to get the solution of UXT from the PDE using the method of separation of variables. If you are interested to learn how to get this solution, you can refer to the textbook.